Welcome. In this video, I'll explain how floating point numbers work and how they are stored in memory. If you already know how integers are converted from decimal to binary, that will help as a starting point, but floating point numbers take this further by also representing fractions, which makes their encoding more complex. That's why some smart people defined a standard. It's basically a blueprint or set of rules that we have to follow when working with these numbers. That standard is called IEEE 754, and the idea is to represent a floating point number in a binary using three parts: a sign, an exponent, and a mantissa. To keep things simple, we'll use the 32-bit float format and look at the number 9.26 as an example. If you want to use the 64-bit version, it works the exact same way, just with more bits, but the calculations stay the same. So let's take 9.26 and split it into 9 and 0.26. We're gonna write it in binary format. Let's start with 9. We always begin with biggest power of 2 that fits into our number. For 9, that will be 8. Since we use the 8, we write down a 1, and we have 1 left over. The next powers of 2 are 4 and 2, which don't fit into our remaining 1. So we write down zeros for both. And finally, 1 fits perfectly into 1, so we write a 1. That gives us 1001 for number 9. Then we move on to the 0.26. We use a similar idea, but with negative powers of 2. So we check 2 to the power of negative 1, which is half. That's bigger than 0.26, so we write 0. Next is 2 to the power of negative 2, which is a quarter. That fits into 0.26, so we write a 1. We keep going to try and make up the exact remaining value, but in this case, 0.26 doesn't fit perfectly. It will actually keep going forever and cannot be represented exactly in binary. We get a long string of binary digits, which translates back to approximations like 0.258972 and so on. So putting it together, we get 1001.0100 and so on. Now we normalize the number to put it into the scientific notation. The idea is to shift the decimal point so that only one non-zero digit remains on the left, which in binary will always be a 1. To keep the actual value the same, we balance that shift by multiplying by 2 to the power of however many steps we move the decimal. In our case, that's 3 steps. Next is probably the easiest step, finding the sign. This is the first block of our float representation. If the value is greater than or equal to 0, it's positive, and the sign bit is 0. If it's negative, the sign bit is 1. In our case, 9.26 is positive, so we set it to 0. Now we move on to the exponent. Instead of storing the number 3 directly, we add something called a bias, which is 127 in the 32-bit format. By doing this, we can represent both positive and negative exponents without wasting an additional bit for a sign. We just add the bias to our exponent, so 127 plus 3 gives us 130. We then write 130 in binary, which looks like this one on the screen. Now for the mantissa. In a normalized binary number, the leading digit before the point is always a 1. Because it's always there, it's called the implicit leading one, meaning we don't need actually to store it. So instead of writing out the mantissa starting with that 1, we just drop it and take the rest of the numbers after the decimal point. It's clever little optimization. Finally, we have our result. We connect all the blocks together, the sign, the exponent, and the mantissa, and there we have it, exactly 32 bits representing our stored floating point number. Thank you.